phasing due to the 0-point geometry spread. But obviously, one wants to go beyond that, and we actually were fortunate to get into a collaboration with another team led by Tim Larman at Flash, who were doing experiments on the system we originally wanted to measure, which was glycine. And with the help of Marco Roberti's calculations, oh, we've got another. You have to put them out. We did a similar experiment in glycine. So in glycine, we are looking at a slightly larger molecule, and we're probing this time not at the oxygen K edge or around the oxygen K edge, we're probing at the carbon K edge in this case. So we're using 2 pulses from the Flash free electron laser generated by their fancy split and delay unit. I won't go into the details of that because I think there's not time, but essentially they're both the same color. They're tuned to be resonant with this absorption feature that you predict when you've made the whole state in the correct hole channel. Here, the pulse repetition rate is 4,000 pulses per second, and it's a magnetic bottle, so it has something like a 40 times higher collection efficiency than in the earlier experiment. So you can actually get better data. And moreover, it's possible to detect 2 electrons in coincidence with this thing, and even in coincidence with the ion fragments. I'll say more about that in a moment. So basically, the glycine was introduced into the interaction region, and the pump probe delay was rolled, and we made our measurements. So essentially, it's the same scheme I just described. So the detection channel is the Auger electrons, but in this case, we detect the Auger electrons in coincidence with a photoelectron of the right energy. And it turns out the right energy in this case, so this is the Auger signal, corresponds to 273 eV input photon. So it's a little bit below the carbon K edge, and that's where you'd expect to find that inner valence hole. And the hole that we're looking at is the so-called 10A prime hole. We'll come to that in a moment. This is the one that's predicted to give oscillatory charge migration-like behavior. And this is what we measure. This is what we measure the whole probability over a relatively long delay range, over 150 femtoseconds, with an initially fast oscillatory period followed by a slower oscillatory period. And this is detecting the Auger electron in coincidence with the correct energy photoelectron in coincidence with a glycine 2+ ion, which is what's left over. And the calculations are down to Marco and his ADC2 B-spline ADC theory. He predicts that in the 10A prime hole state, there's going to be a 19 femtosecond oscillatory period for the charge migration. And he checked that even when he puts in the geometry averaging, that still persists at least over a full cycle, at least over a full oscillation cycle. So just for good measure, here's the sort of the cartoon movie showing how the density moves up and down the backbone of the glycine, and we're probing at the carbon sites here and here. So that's where we're measuring it, somewhere in the middle of the molecule, not at the end of the molecule. And so this is again the result, showing this initial oscillation period followed by a different periodicity. And to understand that better, a windowed Fourier transform approach was applied, and this is what it came up with. So the cone of brightness illustrates where you can actually rely upon the extracted data. And so initially you have a period in the early part of this pump probe delay of around 19 femtoseconds, which is bang on the prediction that Marco made. And then at a longer period, after at 50 femtoseconds, it transfers to a slower oscillation time, something of around 30 femtoseconds, which corresponds to several different vibronic transitions or vibronic modes in the molecule. And so this, I think, is potentially the first evidence of electronic coherence coupling to a vibronic coherence and showing this kind of behavior. Now, that was published last year in Science Advances, and we think it has an impact on a number of different things. It has an impact on understanding radiation damage in materials and in biology. It has an impact on the fundamentals of chemical dynamics. We're delving down into the sort of beyond the Born-Oppenheimer approximation. Also on tests of computational quantum chemistry, because this is real data where everything is happening, including the nuclear dynamics. And I would ascertain it's quite important for atmospheric and astrochemistry, where molecules are exposed to these really broad bandwidth pulses, or at least broad bandwidth radiation. And also because of the relevance to ultra-fast quantum coherence and entanglement and the possibility of chemical quantum control. Now, to take this just a little bit further, an additional set of experiments were performed where different final state ions were correlated with the electron signal. Now, this was an imperfect experiment because the mass resolution of the ion time of flight wasn't high enough to really distinguish between a range of fragments. But we looked at two sorts of groups of fragments, which we think correspond to this OH bond breakage and this carbonyl group breakage. And you see that in both cases, the initial periodicity is the same. It's around 2019 femtoseconds, the electronic period, but then it evolves into different periodicities depending upon which fragment you're looking at. Now, we're going to pursue this further in a beam time that's scheduled for September with better mass resolution. So hopefully be able to fully resolve this coupling between the electron dynamics and the fragmentation. Okay. Now to attosecond pulses. So all of that was done with 3 or 4 femtosecond duration pulses, but attosecond X-ray pulses are now available from free electron lasers using this methodology, enhanced SASE, or XLEAP as it's called. The idea of XLEAP is you take your electron beam and before you go into the undulator, you modulate it in such a way that only a small slice of it has enough of a current and a low enough emittance to laze. And that ensures that you laze on a single sub-femtosecond SASE spike. Now, this is done by, in this early experiment, it was done by energy modulation in a pre-wiggler. Originally, it was planned to actually put a laser into that wiggler. The laser didn't work, so it was proved that the self field in the wiggler was enough to energy modulate the pulse. So though they called it XLEAP, which stands for X-ray Laser Enhanced Attosecond Pulses, Argo Marinelli, who's the inventor of this, or in charge of the demonstration of this, calls it XCheap because we did it without the laser. And then that bunch gets modulated in a chicane where essentially the energy modulation is transferred into a strong current modulation, and then it lasers. And to demonstrate its lasing, we use our old friend streaking, and in this case, it's angular streaking in a circularly polarized field. And so basically, just by verifying that the final electron momentum after it's been streaked is some small fraction of the 2 pi angle it could be in, it demonstrates that the pulse is much shorter by a large factor than the cycle time of the laser. And in fact, you're able to measure the pulse duration, and the pulse durations are a bit of a spread, but averaging in this case around 350 attoseconds. And so that's exciting, and that's now available. It will soon be available not at 120 hertz, but at the new repetition rate of the LCLS2, the superconducting machine. That will be maybe 30 kilohertz initially, and then going up to much higher rep rates eventually. But what's really exciting about this, and I heard the discussion earlier about going to higher energies with high harmonic generation, and I do it. Okay, I do it too. And this point at the oxygen K edge is from my own lab. And so I'm putting it up to show you the difference in the energy of pulses generated by XFELs compared to with HHG. So with HHG, we can generate pulses with an energy of something less than 10 to the minus 6 of a microjoule. With free electron lasers, tens to even hundreds of microjoules seem possible. So in other words, you're generating near transform limited pulses with a large coherent bandwidth, sub-femtosecond duration, with 8 to 9 orders of magnitude higher energy than you can get from high harmonic generation in that photon energy range. And I'm afraid that tells me that if you want to look up here and you need a high energy pulse, then come to an XFEL. If you want to look down in the XUV, and there's lots of interesting science to be done there, then use HHG sources. And I'm going to tell you very briefly 2 demonstrations of this high brightness and high temporal resolution. The first of these was the first demonstration of the observation of a core-excited electronic wave packet in the NO molecule, basically by looking at the quantum interference in the Auger-Meitner decay registered in the time domain through streaking. So I won't tell you the details of this. So essentially what happens is you create, with this broad bandwidth pulse, a coherent superposition of 2 or maybe more core-excited electronic states in the molecule. These would each individually Auger decay, but there's a beat note between the Auger decay of the different channels, and that's registered in the streaking pattern. And what you see, instead of a regular decay over the streak window time, you actually see a kind of a bump due, and there's possibly even a second bump due to the extra state that's also excited. And that was also published last year, just as an illustration of what you can do with these techniques. The other thing which was done was impulsive X-ray Raman, which many of us would argue is an exciting possibility. It maybe has applications to X-ray spectroscopy, because the final state of this Raman process is an excited state of the molecule, of the neutral molecule, but not an electronically not a vibrationally excited state like in conventional Raman, but an electronically excited state, because there's enough bandwidth that you get both the pump and the Stokes photon from a single pulse. And that makes for excitation into these excited states. And we verified that by doing a post pulse in the UV that showed excess ionization when we had the X-ray pulse first, that demonstrated we were exciting into this. And it agreed that the experimental data is this blue curve, and the green curve comes from Antonio Picon's calculations, which sort of tie up quite well with quantitatively with what was measured. And why that's interesting is because of these ideas that Scholl Mukamel has been going on for a number of years now, about the possibility of tracking electron coupling through neutral material systems by exciting an electronic wave packet at one atomic site and perhaps reading out at a second atomic site, and actually understanding how the electronic charge energy is transferred between the two. So for that to be real, this was detecting particles. For that to be real and to really realize the dreams that Scholl has been having, and you know, maybe they're dreams, maybe they're wrong, but we need to test it. One wants to look in the photonic channel, not in the ions coming out, but actually at how the X-ray field itself is modified in the process, because that will be the best way to develop a true X-ray multidimensional spectroscopy, which is the first step towards. So we went to LCLS last May and went not to the TMO end station, which is the one where the other data was recorded, but to the end station upstairs, the Chemrix end station, where we were allowed to run a liquid jet. So we ran a liquid sheet jet of water, and we tried to look for the Raman signal in that system. So we came in with these X-leap pulses, which typically have a bandwidth of about 8 electron volts. They are focused into the water. The liquid is about 2 microns thick, 1 to 2 microns thick. It's very thin, but it has enough interaction with the X-rays that it could, in principle, modify the X-ray beam propagating through. And we actually have a controllable position, so we can move the interaction point into the X-ray focus or out of the X-ray focus, so we can compare low with high intensities, and that was the methodology we used. Unfortunately, in these measurements, we didn't have an upstream spectrometer, so we couldn't look at the spectrum going in and the spectrum going out on every shot. We had to do it with statistics and changing the intensity range in order to pick out what was going on. We also did measurements without the liquid in, and then moved the liquid back in. And it's a wonderful liquid jet system, by the way. It works really well. It's really stable and very nice to work with. So what did we see? Well, we measured the change in the transmitted spectrum when moving into the nonlinear regime. So essentially, we formed the difference between the spectral response in the focus with what happens when you're out of the focus, and that allowed us to look at this sort of map. So what we see are things you would expect to see. This corresponds to the X-ray absorption edge, but down here, about 8 eV below the X-ray absorption edge, we see a feature coming up in the higher intensity shots. And this is exactly what we'd expect to see. This actually corresponds, as I'll show you in a minute, to what you would expect to see in an ordinary Rix spectrum for water, for liquid water. So basically, the bandwidth of the pulse is sufficient that it's sort of spanning across the band of the absorption in water, and we observe an emission feature consistent with the Stokes sideband, which is this guy here, which is growing in with intensity. And this, just for comparison, is a comparison of a conventional Rix spectrum, which is, this is spontaneous Raman emission, not stimulated Raman emission, and you see the feature comes up in the same place, around 526 eV. Now, Laura has done some fantastic work on the calculations behind this. The initial calculations were done in molecular water, but in the gas phase, so not with the corrections for being in liquid phase, but at the density of a liquid of the liquid phase. And so what she predicts is this behavior over the same intensity range that we measured. And there's actually two features, or even three features, that come up in that case. And that's because the gas phase water spectrum is different to the liquid phase water spectrum, and now Laura is going back and is now starting to get some results that hint that we can actually do the liquid phase calculation with some confidence. And the interesting thing is, where the feature is expected to come up in liquid phase water would correspond quite closely to where we see the feature in the experimental data. And again, just for comparison, this is the old Rix data showing that we are seeing a feature exactly where you'd expect it from the Rix. So this is, I think, encouraging. I think it's a first step towards realizing some of these ideas. We still got to interpret a little bit more, but I wanted to share those results with you and sort of make the claim that we think we've seen impulsive X-ray Raman in the photonic channel from liquid water. Okay, I'm going to finish in just a few minutes, but before I do that, I've got to talk about attosecond pump probe, because that's really exciting. And attosecond, oh, this is the happy team. Attosecond pump probe, again, using XLEAP, led by Argo Marinelli. The idea here is to make two X-ray pulses, one to do the pumping, one to do the probing. And it's the methodology I'll describe is essentially the same methodology that was applied in the X-ray absorption ideas. In this case, the way it's done is you make the first undulator section is tuned to, say, well, we'll call it omega. It's about, say, 250 EV. The second is at 2 omega, so it lasers exactly at the second harmonic, and that allows you actually to get into T0 in this case for various electron physics reasons I won't go into. And you then, again, using the streaking to measure the relative delay between the two pulses, using the fact that they're ionizing different gases, and you can control the delay by a chicane, which gives you fairly coarse changes, or by taking in or out undulator sections in this undulator units in this second undulator section. Now, in doing that, of course, you do change your intensity, but that's one of the costs you have to then factor out as you're interpreting the data. And so it was shown that you could actually use this method to get different pulse delays from the two pulses, and that you could actually scan the pulse delay over a range from about 300 attoseconds up to maybe 800 or so attoseconds using just the undulator sections, and then longer delays using the chicane delay. And a first measurement was made in the aminophenol molecule, looking at photoelectron spectrum and essentially characterizing the measured binding energy with the second X-ray pulse after you've done the first ionization with the first, and seeing that actually the apparent binding energy you measure is going to change quite rapidly with pulse delay. And the initial reason for that is that you've got one electron going out slowly and another electron going out fast, and so the second electron overtakes the first, and there's a different effect depending on how they're delayed relative to each other. So in fact, this green curve is taking into account that so-called PCI, post-collision interaction effect. But then at longer times, the theory would have it diverge up to a much higher binding energy change. And in fact, the last point is coming back to something close to the 2 femtosecond point. And that we think is due to the fact that there's actually proton loss. So in fact, effectively, this sits bang on where you would expect the cation without the proton to actually have its binding energy. So that's the first demonstration of the pump probe capability. And then rather before that, it was turned, sequence of this is complicated because there were multiple beam times, but essentially at the same time, we were measuring valence whole wave packets. So in other words, the same charge migration things in aminophenol, and Fernando's already introduced us to some of the calculations on that. I'll just show you the experiments and what they look like. So basically, we're using 2 pulses, probing near this oxygen site. The pump pulse is around 250 EV. The probe pulse is at the second harmonic. And so the probe pulse is able to probe the different hole states that you can open up with the pump pulse. And I'll just show you the results of that. So the blue points are the experimental data. So we were able to do, I think, 9 different delay points and measure a very fast initial decrease in the hole, and then it sort of stabilized and then gradually decayed away. Overlaying on this is the equilibrium geometry, the geometry average data calculated by Marco's ADC, beast by ADC theory, showing that actually we've got quite good, even quantitative agreement between the two. Now, ideally, we have a lot more experimental points. Now, they're really painful to come by because we're working at 120 hertz, and we'd really like to fill in this whole space. And so I think this is already a really exciting achievement. It's showing, I think, something that you couldn't have measured before by any other means. But the future would look to be using the high repetition rate capability to really get high quality data and really clean it all up. And on that note, I want to introduce you to the UK XFEL project, which is a look ahead to a next generation XFEL capability. I mean, whether it's UK or something else remains to be seen. We're trying to get an international enthusiasm about this. But what we're doing locally is looking at how we would achieve transform limited operation across the entire X-ray range, a high efficiency facility, in other words, with a high rep rate CW loaded superconducting LINAC, evenly spaced high rep rate pulses that best match samples and detectors, improve synchronization and timing data with external lasers to better than a femtosecond, possibility to have widely separated X-ray colors at a single interaction point, and a full array of synchronized sources, not only looking at the electromagnetic spectrum from the XUV all the way up to terahertz, but also looking at electron beams, ion beams, and other things that you might want to do radiolysis or other interactions with. And this is a project that's started October last year, runs to October 2025, in which we are attempting to map out how best to deliver that capability. We're developing a conceptual design that will deliver that, but also looking at other investment options. So we're working very closely with European XFEL and LCLS. We visited SwissFEL as well to explore how investing in those facilities could deliver to the UK and the wider world this next generation capability. And we're holding multiple town hall meetings around the UK. The first of those was in Belfast last week. I think it was a great event, and we're looking forward to the next one, which is in Strathclyde in October. With that, I'll finish. Lots of people to acknowledge, both from the work on isopropanol, the work on glycine, and the collaboration with SLAC. With Autonoma, so lots of people there. Laura Rego started the work while she was with us, but now she's in Madrid. Fernando, Gilbert Grell, Alicia Palacios, many, many others. So with that, I thank you for your attention.
I think we have time maybe for one question.
One ultra fast question.
Yes, one ultra fast.
I don't like anyhow, I'll do it like that.
Yeah.
So if I understood correctly, you're in these experiments where you see a change of the frequency from a lower to a higher value, you're not exactly sure what the transition is.
Well, look, it's a coupling. It's not exactly a transition, but I mean,
my question is, would it make sense to use isotopes in this?
Yes, it could. I mean, indeed, that would be a very interesting thing to do, because you might actually, I mean, most of those modes seem to have the carbon-carbon or carbon-oxygen frequencies. So it may be only for the ones where we're looking at the hydrogen fragments would we actually get a good isotopic effect. But no, I like isotopes, as you know. So yeah, we might want to do that at some point. Good idea.
Okay, thank you very much. Thank you. The next speaker is Wilhelm Becker. And his title is Rescattering quantum orbits with negative experiment.
No. Well, let's hope it was.
Okay, thank you very much. First, let me thank Carla and her team for the invitation to this meeting. And she must have carried out a lot of work. And I noticed an unprecedented amount of attention to detail, because when I was first looking at the program, I noticed that obviously in view of my title, I had been allotted a negative speaking time of minus 30 minutes. And so while I was pondering how to cope with that challenge, I noticed it had been changed to the positive time, which makes my job much easier. But still, I would like to ask, can you remind me at least 10 minutes before the end of my talk so that I come to the main topic? Because when I was preparing my talk, the introduction kind of shifted more and more and more to take over the entire time. But I want to make sure that I get to the main topic. Where is my head? Ah, this one. Yeah, okay. Yes. Okay. So the idea to this meeting actually was conceived a long time ago by Heraclit of Ephesus, who stated that in a free translation, a barrel is the father of everything. So we'll see if his statement will be supported by this meeting. Okay, so what I want to talk about is first the derivation of the saddle point method, and then examples of earlier results that have been obtained with it. So that's why that's the introduction, and it became longer and longer because there are many results that I really like a lot. Central topic is how to, it's normally said, okay, you include the relevant orbits. Question is, what are these relevant orbits and what are they not? So this is basically the central topic of my talk, and then I look at this in the context of elliptical polarization. So it's the strong field approximation, and the basic formula is covered by this stuff, but you know it all, it doesn't matter. And okay, there is the, one step further, you eliminated the limit of t to minus infinity, then it looks like this here. And okay, right here, question is what to do with that, because that's where all the problems, the difficulties lie. Normally, these days, most people approximate the underlying stuff by trying to incorporate the Coulomb potential into the action in the exponent. Beautiful review has been given by Carla Faria and Andy Maxwell. And I follow the second approach, using the Dyson expansion in order to expand the exact propagator in terms of the interaction with the binding potential. The saddle point approximation was first introduced in this context by Maciek Lewenstein and his co-authors in these seminal papers. Huh? Okay, here we go. No, it was not working. Let's see. Okay, yeah. So then you get this expansion here of the exact matrix element. The first term has no interaction with the laser field, so we call this the direct electrons. Please notice the direct, in this context, the direct electrons are defined very formally. And electrons that contribute to this term can very well revisit the atom once or several times. This is a different nomenclature because most other people these days define direct electrons as those that do not see the ion again. Here are the once rescattered electrons, and then you can continue, of course, but this has rarely been calculated. And there are some limitations here which are very well known, especially this is the fact that the initial state remains undressed. If you were able to do everything, then of course the initial state would also get dressed, but if you cut off the expansion at any final stage, this is out of the question. Okay, then you also expand here the Volkoff propagator in terms of the expansion into Volkoff states. And then you have this action here. And now the idea is the integrand here is very, very highly oscillating. So you try to evaluate it by finding those ionization times, recollision times, and intermediate momentum where the action is stationary. And that gives the saddle point equations, you know this all. And these equations have many solutions. Each solution defines what we call a quantum orbit. So you have just to figure out these parameters, start time, rescattering time, momentum in between, and then you can construct here the quantum orbits. And they are complex because of the minus sign here. Invariably, they are all complex. The real parts give orbits. And yeah, the nicer thing is that now the problem of doing this 5-dimensional integral has been reduced just to finding the solutions of the nonlinear saddle point equations. And the beauty is this works for any field, for any polarization, especially. I mean, normally if you solve the TDSE, going from linear to elliptical polarization is a big problem, really. In this case, it's not. Just finding the solutions is a bit more complicated. And actually finding the solutions can be anything but trivial. I should mention that a better approach actually is the uniform approximation, which has been pushed by Carla Faria again. Okay, now you have to get these saddle point solutions. And the first starting point is normally just looking at the simple man model. And for this, we have this picture here of the electron trajectories as a function of time, and the intersection points with a real horizontal axis give you the recollision times. I much prefer this picture here, which is equivalent, but much simpler. What's plotted here is the curve, is the integral of the vector potential. So for most practical purposes, this is the negative of the electric field. And you plot that, and then you choose a start time, puts a tangent to this, which reflects the fact that the electron starts with a zero velocity, and determines the intersection points. Here, each intersection point with a curve defines a recollision time. So you see already that there are many solutions. And let me emphasize here again, these facts here, these solutions do not correspond to multiple interactions. because in the rescattering term, it allows only for one interaction with the field, which can be at any time. So it can be here, for example. That means that the trajectory has swept over the position of the ion twice, but this is not reflected in the formulas. So that's important to keep in mind. Okay, so there are many solutions, and we have classified them. This is a complicated picture, so I don't really have the time to go through it. We classify solutions by this multi-index here. The M is the approximate length of the orbit in multiples of the laser period. The beta tells you of whether the electron was liberated in the first or in the second half of a field cycle. And then for each such solution, you still have the long orbit and the short orbit, which is known from harmonic generation. Okay, and so you see we have in general, you have 4 solutions per period of the laser field. Okay, I'll use this multi-index in the rest of my talk, even if I haven't really properly explained it, except to those who know it already. So now let's come to examples. And let me start with the linear polarization. And here is something that is very old, but I like it a lot. The experiments here are 25 years old. Yeah, it's by Hertlein, Buxbaum, and Muller, and it shows the amazing fact that this is part of an ATI spectrum. And if the driving intensity is increased by a mere 5%, here the peaks jump up by almost an order of magnitude. And then if the intensity is reduced again, the whole thing deflates. Okay, what does it come from? We can very nicely explain it with quantum orbits, because as I told you, you have to superpose many solutions. Normally, that makes little difference. Normally, just a couple of them are sufficient. But every now and then, it does make a lot of difference. And so here, then many orbits contribute, and they superpose coherently. Whether they superpose coherently or not depends on the field parameters. Turns out here, this is the case just around the channel closing. And here's another extreme example. It's harmonic generation, but it doesn't matter. Look at this harmonic rate here, how it rises up here in an extremely narrow spike. The spike was obtained after superposing 162 orbits, which corresponds to about 40 cycles. And you need that many to build this up. If you only take 2 orbits, then you get this here, so a mild oscillation, and the more orbits you take, then the higher it rises up. And also implication is 162 cycles for this effect to be seen. Apparently the driving pulse has to be at least 160 periods long. If it's shorter, you won't see this. Okay, next example is a low energy structure. It can happen, as you see here, that you put the tangent here as you should. And now here it touches the curve, which means that the electron returns with a 0 velocity. So that's a soft recollision. And you also see that if the electron starts just a little later, then there is no such interaction anymore. And so which means the 2 solutions, which up to this point have contributed to the spectrum, drop out. So it's a cutoff. And actually, this is just the cutoff of the lowest LES, which, okay, gives the well-known formulas. And, okay, this is just the picture in the field direction at high energies. This here is a complete picture, and it's very complicated. And what's shown here is just all the angle-dependent cutoffs of the various orbits that I showed you before. So you see that it's especially complicated here near 0 momentum. So let me focus on these 2 regions. Up here, this is kind of easy because it's the high energy cutoffs. Normally you only see the 10 UP cutoff, but there are many more, and depending on the situation, you can see them in the spectrum or not. But what's really interesting here is the region around the origin. You see the LES here, this one, and here's a corresponding formula derived in a few lines. And okay, don't look at all these formulas. I mean, they give you the energies as a function of the travel time, and they are classified here in terms of the orbits that I tried to introduce very briefly before. Okay, so I mean, this region here is enormously complicated, but basically everything has been seen. Again, I mean, you see the LES here. Here, this region, the first, the second, the higher ones. You see what we call the fork, which is essentially this one and this middle one. And you see a V structure here, which also has been observed. It's this V here in this region. And so basically remember again, this is a very simple thing. I mean, it's high school physics. It's just the cutoffs of the Simpleman model. Here's a strong field approximation calculation. Doing the integral here, you see this V structure right here. And this also has been observed in a paper which I forgot to write down here. And okay, here's an experiment, the famous holography paper. And actually, you see all of this in the spectrum. Here's a fork, the middle prongs, the outer prongs. Here you also see the spider. Now, the spider is a dominant Coulomb effect. So we have something like it also in the SFA, but there is really no qualitative match. Okay, but otherwise, okay, this is of course due to the amazing, the longer the wavelength, the better all these features develop. Okay, yeah, bicircular fields is another nice example. And here's a calculation of the angle resolved spectrum due to a bicircular field with 800 and 400 nanometers, same intensities, and it's based on a numerical evaluation of the integral. So, I mean, you see here the rescattering rings, and then you see all of kind of stuff going on here for smaller momenta. And I love it because here the quantum orbit formalism allows you basically to decide the origin of any one of these features. So what you have to do is you select some quantum orbits, like here are some for forward scattering, another for forward scattering, here's one for back scattering, and they all give different patterns. And here is what you get if you superimpose all of them. And it's pretty much like the exact calculation. So if you want to know, for example, what is the origin of this feature here? Well, apparently it comes from this orbit. What is the origin of these fingers here? It comes from backscattering. And you can also sketch the corresponding quantum orbits, which is done here. So you can identify, if you want to know, for example, and here, this here, what is it due to, etc. Okay, now I'm coming to the main topic of my talk. This is old again, I'm sorry. This is very old. It's elliptical polarization and the spectrum in the direction of the laser field. And what you see here is that the customary ATI plateau is changed into a staircase. And what's interesting here, how come? I mean, why is it that the cutoff is still there, but it's as a much reduced intensity? This is a calculation for very high ellipticity of 0.5. And the orbits are also sketched here that are responsible. And it's elliptical polarization. So the minor component acts something like a side wind. And for this orbit here, the electron essentially, okay, I forgot to say, what happens is for elliptical polarization, the simplest Simpleman version allows for no returns whatsoever. But the quantum orbit formalism calculates exact returns, and for that purpose, it has to attribute to the electron a perpendicular velocity from the beginning. And the higher this is penalized in the action because the kinetic energy corresponding to this transverse component acts like increasing the binding energy. So it drops very, very quickly. And now this side wind here is, in this case, the electron moves essentially in one direction. So you need a large transverse component in order to compensate this, to allow the electron to return. For the longer orbits, they extend over several periods. So then the effect of this side wind averages out, and you get much higher intensities. Actually, this has been seen in an experiment at the time by Gerhard Paulus and his group. Okay, so this is old. Now, in order to come to the new results, I have to return to linear polarization first. This here is a spectrum for linear polarization in the direction of the laser field. And again, it nicely emphasizes fact that when the quantum orbit formalism was set up, everybody cared about the plateau and all that for high energies. Now it turns out the plateau is the easy part of this, because in the plateau here we get a perfect description of the exact spectrum with just a handful of orbits. And it's 20 here in this picture, but it could also be fewer. But where things are really getting messy, this is here for low energies. So there are all kinds of orbits drawn in here, and still the fit to the spectrum would be fair, but not as good as in the high energy part. And here already, we need to take some orbits which are beyond the simple band model, because the travel time is very, very short for linear polarization. It's these here, these pink orbits. They have a difference between ionization and rescattering time, which is very, very short. Okay, now let's turn to elliptical polarization. And here's a calculated spectrum by doing the exact integration. And you see how this feature here develops. When the wavelength increases, you get this ellipse here in the middle, which pretty much follows the shape of the vector potential. And up here, the rings are the normal rescattering stuff, but the real interest here is in the middle for low energies. And so this is a numerical calculation, and the question is how to get it. And for linear polarization, if you have a solution of the saddle point equations, given here, the start time, the return time, then it's easy to show that there's a second solution, which is written down here, which is a period minus the complex conjugate and of the ionization time and the rescattering time. And these solutions have the same imaginary parts and gives the same 10 minutes. Oh, great. And gives the same contribution to the spectrum. But these start solutions have a negative travel time. So we just used to discard them. And got a fairly decent fit of the spectrum. Now, for elliptical polarization, the statement here is no longer true. The second solution here is no longer a solution, but there is a corresponding solution that develops out of it. And it turns out the second solution is now the dominant one. If we only take the standard solution, this one here, it doesn't really yield the effect that we are after. However, on the contrary, the start solution gives a very good description. And if you plot the contributions here as a function of energy, you see that very clearly, that already for a small ellipticity, 0.1 here, this one is much more important than this one by up to 2 orders of magnitude. So we need to get this new solution in order to be able to explain the spectrum in terms of orbits. but it has a negative travel time. Okay, these solutions are complex and they have large imaginary parts, which means that considering the real parts as interpreting them physically becomes more and more questionable. So it's not, so here, this is again, I showed you this already. And here I plotted the real and imaginary parts of the saddle point solutions. So here is a standard solution for linear polarization is this, and here's the other one, which is the same, that has a negative travel time, and which you normally discard. But for elliptical polarization, you have now to take the two of them, and actually this start solution here becomes more and more dominant. And the real part of the time difference is negative. Okay, did I miss any? Yeah, comparing this now, the new solution, here's the result again of the numerical integration. And here's the result of this new solution of the saddle point equations, and it gives a very good fit of this. So it's really needed. Now this brings up the question of, well, which solutions do you have to include and which ones can you drop? Which is an open problem. I mean, I recall that in the old days when the Levenstein model was formulated, I just refused to take it seriously because I figured this is a mathematical adventure. And because, okay, let me, this is here direct electrons for single for in one dimension. And so here it's, you can easily follow any step. The original integration contour is along the real axis right here. And here are the saddle points, 4 of them, here, here, and here, with up, which are complex conjugates. Now, what you want to do is to reroute the contour so that the dominant contributions are given by the saddle points. And for that, you want to suppress the oscillations in the integrand. So you want to have a constant imaginary part. And now here you can follow this in all steps. Turns out that in order to achieve this goal, the contour has to go this way, up here, then down here through the saddle point, up here, down here again, and so on. And these contributions here cancel. You also see immediately that there is no way of reaching the saddle points here in the lower half plane, because you have to stay away from the yellow parts where the real part is large. You want to pick up the dominant contributions from here. So there's no way these solutions here are ignored. Now, when this picture here is valued up to some critical intensity, some critical energy of the electron, and if you increase it more, then the topology changes abruptly. And again, now the story is, again, you cannot get into the negative half plane here. There are 2 saddle points here. And if you look at it more closely, you see you have to include this saddle point and ignore this one. Actually, this is automatically taken care of by a unified approximation, but that's kind of more complicated. So this is an example here where you can see everything. Now, the mathematical adventure of the Levenstein model and the 2-dimensional saddle point integration is here. You have to deform a 1-dimensional contour into the complex plane. This can be done on a sheet of paper. If you integrate in 2 dimensions, then the origin contour is a hyperplane in complex space. Complex space then is 4-dimensional. So you have to deform this contour into 4-dimensional complex space. And that is where I am completely lost. And everybody I talk to as well. So it's an open problem, and in rescattering in general, you have to find the proper solutions and to drop those that you don't want to have, basically by trial and error. And so in the case I showed you, we noticed that you have to include a solution that normally, by arguing that it corresponds to a negative travel time, you don't want to have. but you need it here. Okay, so conclusions are that quantum orbits account for a lot of stuff, nice stuff that you can see in ADI for all kind of laser fields. But you have to be careful in selecting the relevant saddle point solutions. And we found here kind of a new structure in rescattering in elliptical polarization, which has a shape like a coffee bean. If do I have 2 more minutes? Oh, great. Then, I mean, I forgot to mention that this Dyson expansion in terms of the binding potential is perfect for a short range potential. So basically, after the first step, you got almost perfect agreement with the solution of the TDSE. For a Coulomb potential, of course, this is no longer so. Actually, if you try to go further, you even encounter divergence problems. And the question is, of course, what about the entire series? Is it even going to converge? And these are open questions, but you can look at the Coulomb scattering without the laser field. And so this is just interaction with the binding potential here. And here are the higher order Feynman diagrams. And the lowest one can be calculated in a few lines. And it gives a correct, exact cross-section. And if you were to calculate also the higher order terms, you would have to get around the divergences, and the result would get worse and worse and worse the higher you go. However, if you would sum the entire series, then miraculously all the divergences are absorbed into one phase, which is divergent, but cancels out of the total cross-section, and you recover the first order result. So that's the upshot. And that's always in the background. Now, of course, for a laser field, what you have to do is very simple. You just have to replace the free propagator by the Volkoff propagator, drawing a double line here, that's all. On the other hand, of course, the calculation is becoming tricky. And the hope would be that, again, you can stop at some finite order. And of course, you can't. The answer to this question is negative. But I feel that the normal Coulomb problem always lurks in the background below the surface. And so the Coulomb potential might allow one to find some effective interaction or some effective order where you can terminate the series and get a nice result. But okay, this is wishful thinking maybe. Okay, thank you very much.
Thank you very much. One question? Then I think
Well,
we
everything
can
was
finish.
clear, I hope.
Thank you very much again. Our next speaker is Robert Moshammer, and he will talk about habit-like experiments with molecules.
Thank you. Okay, thank you. First of all, thanks, the organizer. I'm happy to be here. It's always a pleasure. And it's in particular pleasure after these 3 years of, so thank you. First of all, this talk will not last 30 minutes. Don't be afraid. I'll be shorter. And I'm going to come back to in principle, the first talk this morning, Fernando, Rapid, and I will present you results that we got during the last 1, 2, 3 years in maximum, because this is a new experimental setup that we built up in our institute in Heidelberg. So it's a high harmonic source. We create harmonics. On the lower left, you can see a typical spectrum in argon with a driving laser, a very powerful one, 100 watt, 40 femtoseconds, 30 femtosecond pulse lengths. And we inject these pulses into a Coltrane's or reaction microscope and do measurements, electrons, ions in coincidence. And the whole thing, in addition, is stabilized in order to get a good temporal resolution. So typically we are safe in the order of, let's say, plus minus 100 attoseconds. And this was tested over not only 30 minutes, but in fact, over many, many hours. So it's stable. And I'm going to present you a few results. So this is, so to say, the outline. First, some molecules. There is no pointer here. Is there another laser? No. Typical molecules. I will briefly discuss results and also problems, questions, and then I come to the final talk, to a final subject where we think we can interpret a little bit more because the molecule is much simpler, H2. Okay, let me start with the first topic, dimer, argon dimer. So we look to the photoelectrons in the presence of the high harmonics and the IR, and we can select now the electrons from the monomer or from the dimer. And as you can see here, they are overlapped both, and you see a tiny shift. They are shifted by 200 millivolts. And this tiny shift is essentially the, should take this picture here, the binding in the argon dimer. And there's a small difference in the binding energy between ground state and in the neutral and in the cation. And this small difference is reflected in a small shift in the photoelectrons. So far, so good. And then you also can measure, for example, the sidebands here, and you see that they oscillate nicely, and you can extract phases. And then you can compare the phase that you measure for the monomer and for the dimer. And you get a curve here. Okay, it suffers a little bit from statistics, but there is another paper on krypton, and it's also discussed what the subject here is. And it's in principle that you populate in the cation here a superposition of grade and ungrade bound states, and this leads to a small shift in the phase, and then therefore all small shift in the time delay. So this can be well understood. So let's go one step further and look for nitrogen. And for me, this is a horribly complicated molecule already, so I get afraid. And we have two channels here. These are just the ion spectra, pure ionization. You remove an electron molecule, the cation stays stable, and fragmentation. Let's look first for the pure ionization. And then you ionize now with our laser pulse. From the neutral, you end up essentially 3 different states in the cation. And I think these are essentially the same that you showed this morning, right? And then we can look to the electron spectra, for example, only the XUV. No IR. And this is the blue curve. And then we get already lost. Problem is our pulses are a little bit too short. The spectral bandwidth is a bit too broad. And the separation of the harmonics, because it's a 1000 nanometer laser, is reduced to only 2 eV. So, and if you now superimpose in addition the IR, what is the sideband? What is the main peak? No way. Nevertheless, you can look for some oscillation here. Wait a second. You can look for some oscillation, and I tell you, we don't see anything. It's simply everything smeared out because we miss spectral resolution. Or in other words, our pulses are too short. The driving pulses are too short. There are other nice examples, and I think you also showed one of these this morning. Here's one example where they use longer pulses, longer driving pulses, and the spectral bandwidth is smaller, then you can resolve different states. Okay, then we thought, let's take a trick, make a trick, and let's look at these guys here, the dissociation here. Because there we get more information about the final state. We not only have the electron, we also have in coincidence the molecular ion, the fragment. And then if you look what's going on, if you come from ground state, you ionize, you dissociate, and what is now the new quantity that is conserved? This is some energy. The sum energy of the photoelectron plus the kinetic energy of the fragments. So you should see when you plot electron energy versus Kerr diagonal lines, and here they are, very nicely. This is XUV only, and now let's do the same job with the IR in addition and hope that we see some sidebands. Here they are, nice sidebands. And what is more important even that in the fragment distribution for the Kerr, we can even distinguish different vibrational states that are formed in this C state. This is at least the idea that we have about the mechanism. So what we do is we remove an electron, we end up with the XUV, we end up in the C state. The C state is a bound state. It lives long enough such that these vibrational states are formed, and then they decay or they dissociate along the D curve. Then you would say, okay, photoelectron is emitted, molecule fragmentation is coming later. And in the sideband now, we should see nice oscillations, like rabbit. Let's do it. Nothing, flat. We don't see anything. We can even select certain vibronic states in the C state. We don't see any sideband oscillations. Okay, then we were kind of intrigued and tried a little bit more. We did the same experiment and we created high harmonic with a second harmonic of the IR in order to make the separation between the harmonics larger. And here you see, for example, for argon, one main peak, another one, now they are separated by 5 eV, big enough to be able to resolve the sidebands. For pure ionization, this works now. We can resolve the sidebands, we see oscillations, everything fine. So we thought, okay, let's go next step and do it for dissociation. Again, nothing. We don't see any sideband oscillations at all. And to be honest, I give this question to you. I don't know exactly what is going on. Is there any kind of loss of coherence, or I cannot say. It's unclear up to now what is the reason for this missing oscillation in the sidebands. And it's just an example that it's not always that simple. You look at something and understand it. This is an example where we tried even hard and we don't understand it at the end of the day. Okay, let me come to another subject, which is easier, H2. It's only 2 electrons and one remains bound. And I'm going to talk about emission control and entanglement. And what we are doing is the same. Here are the relevant potential curves for H2. Ground state is not so important, and you have 2 states in the cation, a bound one and a dissociating one. What may happen now that already just with the absorption of 1 XUV, you end up in a dissociating state here, called ground state dissociation. And from now on, I'm looking only to the case where we ionize the molecule and we get fragmentation. So we look to this process here. H2 is ionized, a neutral and a proton and an electron. Only dissociation, okay? Okay, this is the simplest pathway here. And we again have to look to these lines, diagonal lines, energy conversion, to look for sidebands, because otherwise everything would be smeared out. Okay, now, for example, a typical sideband, you would say, the photoelectron absorbs 1 XUV plus 1 IR, right? These are the sidebands here. You see them nicely. But what can also happen, it is the same sideband here, the same band. It can also happen that you remove an electron, you have ground, it remains bound, and then the bound molecule absorbs an IR. At the end, you cannot distinguish. You have the same energy, There's no way to distinguish. So for this case now, the definition of sideband is getting kind of questionable. We don't know, because we don't know who the photon, the IR photon is absorbed, in the bound electron or in the emitted electron. And the same holds for the main lines here. These are the main lines. You can have these ground state association, as I said, but it could also be that you have a channel like that. Okay, it's a little bit less likely, but with the IR intensity, this is possible, and they overlap. Okay, what are the consequences? And the consequences are, you see this kind of different pathways in the angular distribution or in the relative angular distribution between the particles. So what I'm going to discuss now is the electron emission in the molecular frame. So we are sitting on the H2 plus, so to say, and in the H2 plus, the proton is going that way, the neutral is going this way, and the question is, in which direction is the electron going? Is it going towards the proton or in the opposite direction? And this is what we define here as an asymmetry parameter, just the angle between the proton and the electron, and we correct for the recoil of the emitted electron. So we are sitting in the center of mass of the H2 plus. And if you plot this, then we see a pretty strong asymmetry, depending on the kinetic energy release. So for certain kinetic energies, the proton and electron go in the same direction. For others, they go opposite. And now this is, as I said, an asymmetry in the molecular frame. So, and these are we are looking now for these kind of bands here only. I selected only cases where main bands, so to say, where the total number of photons is odd. This we know. And what is important now, this is an asymmetry not in the lab. So if you would look sit in the lab frame and would look where's the electron going, left or right, would be completely symmetric. Our fields are symmetric. The same for the proton. But if we ask in which direction is the electron going with respect to the proton, then we see the asymmetry. So it's a pure two-particle asymmetry. And you have to measure, in order to see it, the electron and the ion in coincidence. Okay, and I'm going to discuss this now in terms of parity, so to say. And the parity tells us something about the spatial behavior of a wave function. For example, this is an example. You can have either positive or negative parity. And for example, for the bound electron, the electron in the H2 plus, positive parity would be if I write it as a sum of electrons sitting on the left or electrons sitting on the right with a negative and a plus sign here, and the same. I can change the signs here, and this way then we get an asymmetry in the final state. Electron is sitting on the left or electron is sitting on the right. But this makes only sense if I also have an external axis, so to say, or a direction, which I don't have in the present case. But I can write down the same kind of scheme for the photoelectron and then add kind of probabilities like electron left, proton left, plus electron right, proton right would be positive asymmetry and vice versa. And so we have to look to the parity of the photoelectron and the molecular ion in the final state in order to understand our asymmetry that we measure. And that's what we did. So as I said, we look to a channel where we absorb an odd number of photons, either one XUV only. This is this channel here. We start from the ground state. Both electrons have positive parity. We emit the photoelectron Ka by absorption of a photon. It flips the parity. But the ground state is still an S sigma remains positive. So in this case here, we get the bound electron is positive, the photoelectron has negative parity, and the molecule dissociates. So this is our pathway. And I told you we cannot distinguish this pathway from that pathway, where we absorb again one XUV and two IR photons in addition, one on the photoelectron and one on the H2 plus. And if you do the same scheme now, then you end up in a final state. You just have to count the parities here by photon steps. You end up in this state here, beta minus plus. And since we cannot distinguish the two, we have to add them up coherently. That's it. Pathway 1 plus pathway 2, you get this sum. And from the experiment, we can even extract the parameters alpha and beta. So these are parameters that we can measure. And now we go into our simple model description, and then this is our wave function here. And then you can write down, calculate the asymmetry. We could do this ourselves, it's not complicated. And add in addition WKB phase for the motion of for the dissociation of the H2 plus. This is the formula here, and the dash, the black line here is what we calculate. Perfect. So we indeed create this type of state in the final state, which is an entangled state. So we have these two particle states, and we cannot say where we are. For alpha and beta equals 1, this would be in kind of a Bell state. But be careful what I'm talking about, this kind of entanglement. The plus and minus is a parity. So this is not an independent observable for each particle. So the parity itself of a single particle doesn't tell us much, right? It's even hard to measure. So, but nevertheless, this looks like a Bell state here or entangled state. And in fact, it is. And here I show you this asymmetry here now as a function of the electron energy and the Kerr. And now you see that the different bands, either with an odd or an even number of photon, and you see that this flips here. The asymmetry flips depending on how many photons are involved, either an odd or an even number, but we very well can reproduce this. Okay, but there's even more. And this is, we can also change the phase between the XUV and the IR. So we have an additional knob. It's here. And this phase indeed enters here in this wave function. And then you can look at this asymmetry or the entanglement, if you want, as a function of the delay. And that is shown here. And also in simple simulation, very good agreement. So we understand what we are doing, and we think it's kind of, we create a kind of an entangled state, which we can control somehow, either by different intensity of the IR or by the phase between the IR and the XUV. And now you can ask, what is it good for? I don't know. It's kind of a Bell type two-particle state. I think this is a kind of entanglement, and it might be even a playground for quantum engineering. I have no idea. And I think it's also now a good takeover to Mark Fracking's talk, but I guess he will talk about this also. And with this, I thank you for the attention.
Yes, ma'am.
The question maybe this kind of comment. We should really compare notes because we have done almost exactly the same nitrogen experiments like this with pulse parameter.
And
we definitely see relative oscillations for the fact.
I would be interested to know what you did and what we did wrong. But that's good to know, good to hear, because it was really kind of it's puzzling, for us.
I have a question. So this entanglement is the result of mixing two states. One of them is created by AttoChem and just one.
Here you see these two pathways. Yes,
The one needs 1 2B and 2 infrared.
exactly.
But I guess that for the second one, the probability is much smaller.
Yeah, this you can tune with the IR intensity, right? If you tune your, for example, this process here is very likely to happen. Here you have a huge cross section, right? So and then you can make it. You can with the intensity you can tune it. I don't know if you can really make it that both amplitudes are exactly the same, but you have a knob, and be careful what I did not tell you, because this is a picture photons. There is no time, right? But our pulses have a pulse duration. So if the pulses are long enough, then the wave packet that we create here has time to travel out and then absorb another photon here. And we see, for example, differences for H2 and D2. And we also see differences if we make the pulses shorter or longer. So this is, it's only, yeah, it's not the full story, so to say.